Hi everyone, I'm Dan. I'm going to be talking to you about local testing for multiplicity codes. This is joint work with Amnon Tashma. So quick recap about local testing. We have a code, we have a word, and we want to test whether the word is in the code or far away from being in the code. We want to do this while querying the code in very few places. So we query it in, say, q places and return either 0 or 1. And if the word is in the code, we always want to return 1. If it's not in the code, we want to return 0 with reasonable probability, say something proportional to the distance between the word and the code. One of the first families of codes studied in the context of local testing are the Reed-Muller codes. These can be thought of as the set of evaluation tables of polynomials of low degree on the entire space Fp to the m. So we think of a code word as a function from Fp to the m to Fp, and it's in the code if it's consistent with some low degree polynomial. There are two long lines of work studying this local testing problem. One of them in the low degree case as part of the PCP literature, and another line of works in the higher degree case. All of these works basically analyze the same test, which say, pick a random small dimensional affine subspace, restrict to it, and check if the degree when restricted to it is also smaller than d. We call this the dimension k test or k-dimensional test. And we just pick a uniform k-dimensional affine subspace. Now, because xi to the p equals xi in Fp, any function on Fp to the k is equivalent to a polynomial of degree at most p minus 1 times k. So for the k-dimensional test to be interesting, p minus 1 times k needs to be larger than d. Or in other words, k needs to be at least this testing dimension that's written here. Now the state of the art says as soon as the k-dimensional test is non-trivial, it's actually a good local tester and nearly optimal soundness. So we can look at the theorem of Kaufman and Minsel from just a few months ago, which tells us that the k-dimensional test is an optimal local test up to a loss polynomial in the size of the field. So what are multiplicity codes? These are generalizations of Reed-Muller codes that include not only the value of a polynomial, but also the value of its low-order derivatives, where the order is taken up to some parameter called s. Now we think of a word in the multiplicity code, again, as a function from Fp to the m. Now it's to some larger alphabet, where the larger alphabet consists of many copies of Fp, which are indexed by weight less than s m tuples, where we think of these tuples as telling us the directions relative to which we took our derivatives. And we say a function is in the multiplicity code if it's consistent with the values of a polynomial and its derivatives everywhere in Fp to the m. So similarly to Reed-Muller codes, multiplicity codes have good local properties. When we want to define restriction, we need to be a bit more careful because for multiplicity codes, the size of the alphabet depends on the size of the space we're in. So we need to compose with a chain rule map. For example, if we want to know the derivative of a multivariate function at a point when restricted to a line, it's the same as taking its various directional derivatives and adding them up, taking a linear combination of them, where the coefficients are the coefficients of the line that we restricted to. So when we define everything properly, these codes are locally correctable with an algorithm similar to the local correction algorithm for Reed-Muller codes. And these were originally used, that multiplicity codes were originally used to construct locally correctable codes with rate close to 1, and later they appeared as part of the construction of constant rate, low query, locally correctable codes. So what about testing multiplicity codes, local testing? So analogously to Reed-Muller codes, any function from in the multiplicity setting is equivalent to 1 of degree at most k times p minus 1 plus s minus 1 times p. So again, this test is only interesting when the degree parameter d is smaller than this value. Compared to Reed-Muller codes, for large s, this degree bound could be much larger. So we could hope that the k-dimensional test is effective up to much larger degrees than in the Reed-Muller case. So this was studied in our previous work together with Salama, where we showed that for the line test, the k equals 1 test, it's not effective. It's not more effective in the multiplicity case than in the Reed-Muller case. Whereas if we go to k equals 2 already, then it is a good local test up to a degree bound that's pretty close to the naive bound of dks described in the previous slide. Yeah, so we show this with soundness that's pretty poor. It's p to the minus order s. So in this work, we generalize the previous result to a general k-dimensional test. We improve the lower bound on the effective degree range in the k equals 2 case to what we believe is the right degree, though we haven't been able to show a matching upper bound. And we use a different proof technique that we think is stronger. So even our proof of the original k equal 2 result is different in this work. So this is what our theorem looks like in this paper. For any degree parameter d that's smaller than this optimal or naive degree bound dks minus s minus 1, so anything where the gap between these two degrees is at least s minus 1, the k-dimensional test is a good local test with, again, the same soundness, p to the minus order s. So just to see this a bit more graphically, we had this bound ps minus 2, where we know that up to this bound, the test is a good local test. And by the naive degree argument, we knew that at degree p times s plus 1 minus 2, it's not a good local test. And in between them, we didn't know whether or not it's a good local test. So this is all in the k equals 2 case. So we shortened this interval of uncertainty to length s minus 1 in this work. Okay, so let's talk a bit about how we go about proving this. So given a polynomial, a multivariate polynomial, restricting it to a k-dimensional subspace is the same as modding out by m minus k linear relations. So we introduce new equations like x1 equals 3 times x2 minus 7, and we can simplify the expression and get a new expression for the polynomial restricted to this subspace. So for example, if we look at x to the 3, y to the 5th, and restrict it to the line x equals y, this gives us x to the 8th, where if we're working over f7, say, then this would be the same as x squared. So this is an example of a line where the degree of the polynomial drops by a lot, even though we know in general that in the Reed-Muller case, there always exists a line where the degree reaches the optimal degree we could hope for. So the question of local testing becomes, does the polynomial's degree reduce under many restrictions? And we're also interested in the cleaner question of characterization, which is, does the polynomial's degree reduce under every restriction? So does there exist a subspace? Does there exist a subspace where the degree is larger than d? So for multiplicity codes, we need to work with a different basis of monomials than we do in the Reed-Muller setting. This is because, you know, a polynomial like x to the p minus x in the Reed-Muller setting, it's just the zero polynomial. But because it has non-trivial derivatives, in the multiplicity case, it's a valid polynomial. So which polynomials do evaluate to 0 together with the derivatives on the whole space? Well, if we look at the polynomial xi to the p minus xi, it's 0 on the whole space. And if we multiply s of these, then we get something that's 0 to order s on the whole space. And that's the same goes for linear combinations of these multiples. And in fact, in our previous work, we showed the converse. It's basically if a polynomial evaluates everywhere to 0 together with its derivatives, then it's a linear combination of these type of polynomials. So we can just take as our basis all monomials where the sum of the degrees, the integer parts of the degrees divided by p is less than s. Because if the sum of the degrees divided by p is equal to s or larger, we can always subtract a multiple of one of these polynomials and reduce the degree of the polynomial. So this is the basis we'll be working with. And basically, when we're looking at things algebraically, saying the polynomial has degree at most d is the same as saying that when written in this basis, no monomials with degree larger than d are involved. So we don't need to think about the table and its values. We just need to think algebraically. So we adopt the technique introduced in the paper of Haramati Shpilka Sudan in 2013 called canonical monomials. The idea is, because these codes are affine invariant, we can first use affine invariance to convert the polynomials to a convenient form, to a form that's easy for analyzing, and then show our local testing in that form. I'll just make it maybe clear. By affine invariance, I mean that if we take a code word in our code and compose it with a linear map, then we get another code word. When doing this for multiplicity codes, we have to be a bit more careful and apply some sort of chain rule again, but it does work. So let's go back to the Reed-Muller case. This isn't how they define it, but we can define the canonical monomial of a polynomial p to be the maximum over all linear maps of the maximum monomial of the polynomial composed of that linear map. So basically, it's the highest monomial we could see, and this is according to Deglec's ordering or something. The highest monomial we could see in all polynomials achievable by taking our polynomial and composing it with a linear map. So what they show in their paper is that there's basically only one possible form for these polynomials in the prime field case, which is x1 to the p minus 1, x2 to the p minus 1, and so on until just the last variable gets whatever is left of the degree. So basically, we can always manage to smush the degrees all the way to the smaller variables as much as possible. Something worth noting is that when analyzing these canonical monomials, only the homogeneous part matters. This is because since we're looking at Deglec's ordering, anything of the highest degree will always beat anything of a lower degree, and things of lower degree cannot affect the highest degree. So we know our canonical monomial will be of the degree of the polynomial, and the question is just which monomial in that degree it will be. So we only need to look at the homogeneous part of the polynomial. So the way they prove this is in basically two steps. The first one is that they prove it in the two-variable case. So they just show you can move degrees from x2 to x1 as much as possible. And then they proceed inductively. They show that you can move all your degrees from x3 to x2, and then from x2 to x1, and so on. And the only way for you to not be able to move anything anymore is if your polynomial is in this specific form. The two-variable proof is pretty simple. The way it works is you take a linear map that just shifts x2 by a multiple of x1. So you shift it by z times x1, where z is some parameter we'll choose later. And so we look at the coefficient of our target monomial, say x1 to the p minus 1, x2 to whatever is left, or x1 to the d if d is smaller than p. And we look at the coefficient of this target monomial as a polynomial in z. Now, if we're in the homogeneous case, then we can write out our polynomial as sum of alpha I times x1 to the I, x2 to the d minus I. This coefficient polynomial cd of x to the d, I'm looking at the d is smaller than p case, so we should be able to transfer everything to x1. This coefficient polynomial is just sum of alpha I z to the d minus I. Now, this is a polynomial that's non-zero and of degree smaller than p, so it's non-zero for some selection of z. Now, this can be generalized to the d is greater or equal to p case as well. It's not very different. So what happens when we try and do the same thing in the multiplicity case? Well, if we look at this polynomial x1 to the p, x2 minus x1 to the x1, x2 to the p, this polynomial is immune to linear transformations. If we compose it with a linear map, then we just get the same polynomial multiplied by the determinant of the linear map. So this shows that for this polynomial, even though x1 to the p plus 1 is a valid monomial in the multiplicity setting, we'll never be able to move all our degrees from x2 to x1. And this was the same polynomial that we used as an example showing that the line test is not a good test for multiplicity codes in our previous paper. Okay, so why does this happen? This happens because our polynomial CD of z is still not the zero polynomial, but it always evaluates to zero. This is because it is divisible by z to the p minus z, which can happen because our degrees are larger than p. In fact, in our case, it's exactly equal to z to the p minus z. So the corrected version of the two-variable lemma that we show is that we can always smush the degrees all the way to x1 up to a loss of s minus 1. So we can achieve x1 to the e1, where e1 is at least d minus s minus 1. And again, there's an analog of this for the d is greater than the maximal degree x1 can have case, which is similar. So the way that the main idea in the proof, which is maybe the main new observation in this paper, if we look at the coefficient of cd minus 1, so the next monomial after the one we were hoping to achieve, it's the coefficient of x1 to the d minus 1 x2. This polynomial is the Hasse derivative of cd. Now, if you're not familiar with Hasse derivatives, in our parameter regime, it's basically the same as a normal derivative multiplied by some constant, so you can just think of a regular derivative. So if both these polynomials are divisible by z to the p minus z, this implies that z to the p minus z squared divides cd. This gives us a lower bound on the degree of cd, which due to the form of our basis gives us a lower bound on s. So if we think of things backwards, we could say that if s is not too large, then we can't have a large power of z to the p minus z dividing cd, which shows that at least one of these polynomials is non-zero for some z. Now, this is just the example of the case of looking at two of these polynomials, but in the general S case, we could be looking at 5 of these polynomials, and they'd all be derivatives of each other. And if they're all divisible by z to the p minus z, this means this gives us a stronger lower bound on the degree. Okay, so again, this previous discussion focused on the case where we can hope to transfer all the degrees to x1. If d is larger than ps minus 1, then x1 to the d is no longer a valid monomial in our basis, and then we need to analyze different coefficient polynomials. So the example we could look at is the case where k is equal to 2, and the degree parameter d is just the highest thing it could be, the highest possible degree for a two-variable polynomial, which is 2 times p minus 1 plus p times s minus 1. Now, the legal monomials have a very special form in this case. They're very constrained. The power of x1 needs to be p minus 1 plus some multiple of p. So there's just very few legal monomials. And in this case, the coefficient polynomial which we're interested in, which is cps minus 1, cannot be divisible even by 1 power of z to the p minus z because of the spacing between its coefficients. Now, so the monomials which are non-zero have spacing of p between them, which means they occupy different residues mod z to the p minus z. And because we don't have too many of these, that means they can't cancel each other out. So we'll be left with something non-zero mod this polynomial. So in this case, even though the degree is large, we can't even be divisible by z to the p minus z once, which means we can guarantee that we can achieve the highest monomial we could hope for. Okay, so from this result, it's pretty easy to show what we call characterization. That is showing that there's at least one subspace where the degree is large. The way we do this is we first transfer f to this canonical monomial form, and then expand it out as a polynomial in x1 and x2, where the coefficients are polynomials in all the other variables. If we look at the polynomial f of e1, e2, for e1, e2 equal to the e1, e2 appearing in the canonical monomial, the coefficient of this coefficient polynomial is a polynomial in x3 through xm, and we can show that all its degrees are smaller than p, and it's a non-zero polynomial, and by the Schwarz-Zippel lemma, for some substitution of x1 through xm, we can plug in these values and get a non-zero value, showing us a restriction to a subspace of dimension 2, where this polynomial has high degree. And this same argument works for general K. Now, to actually show testing, we use a dimension reduction lemma that appeared in the Harmati-Spilka-Sudan paper of 2013 as well. What they show is that the k-dimensional test has soundness at least 1 over p when k is m minus 1. So if we have a function from f to the k plus 1 to fp with degree larger than d in the relevant parameter regime, then the k-dimensional test rejects f with probability at least 1 over p. Now, it's worth noting that this lemma is basically the main property of Reed-Muller codes used in the soundness analysis of Kaufman and Mintzel just from a few months ago. So this is an important lemma, and we managed to generalize it to multiplicity codes using the canonical monomial form with 1 over p squared rather than 1 over p. Unfortunately, this makes the Kaufman-Mintzel type analysis not really work. Maybe it's possible to show something better than 1 over p squared, but that's what we managed to show. So let's discuss like what problems are still left open. There's a degree gap that I mentioned earlier. There's a degree up to which we know that local test is a good one. And there's a degree where we know just by the naive argument that it isn't a good local test. And there's a gap of s minus 1 between them. We suspect that our lower bound is the correct one, and that's for 2 reasons. One is that our current proof method very much stalls at this value, and that's because if you look at powers of x1 to the p, x2 minus x1, x2 to the p, if we raise it to the power k, then this gives us a polynomial with k degrees that cannot be moved from x2 to x1. Also, for some special cases, we have examples showing, a polynomial of degree d that's lower degree on any plane, for instance. And these polynomials are exactly in the right degree for our result to be tight. So we suspect that the degree bound is tight, but we're not sure. Additionally, we can hope to improve the soundness of this test. So the soundness we show is pretty poor. It's p to the minus order s, where the morally correct soundness should be p to the k, similar to the Reed-Muller code soundness analysis. So that's something that can still be improved. Additionally, all our results rely on this technical assumption of s being smaller than p. And it's really interesting, I think, to find out whether this condition is necessary. Okay, thank you very much.